In this video, we're also just going to look at deriving and also working with the kinematic formulas. These are not new formulas. These are formulas that you use from your high school, maybe. Um, One of the most important one that you did, obviously, maybe in your grade 9, I think it was this triangle where you had your d, your time here and your speed. Okay, and you use this one if you had an object moving at no acceleration, exactly no change in velocity, or should I say no acceleration. So we use this triangle to get all your velocities, your time, your distance, whatever needed. Okay, we're going to employ that formula again. So it's going to be d is equal to v times t. So yes, we do have this as one of your kinematic formulas, and we also have v final is equals to v initial plus acceleration change in time. So it depends on what you're looking at. For instance, if you are working on projectile, then your acceleration is going to be, or should I say, if you're working on free falling object, your acceleration is going to be 9.8 meters per second square because it's acceleration. So that is not all. You have another kinematic formula, and it is v final, one of the important one, my favorite, is equals to v initial squared plus plus 2 displacement. Let me just call it d, not d. Let me just call it change in y. This can be change in y, change in x, depending on what axis you're working in. And also we have another one that is like d is equals to v initial plus v final all over 2 and uh, times time. This one is more of the same as this one. This just we use this to get your average velocity exactly. So d it can be written as like v average time. So this is exactly the same formula. Okay, I also have another kinematic formula. We have another one, and that's like displacement. Let me just call it change in y, as I've been change in y. This, for example, purposes, not like displacement is always change in y, it just depends on the axis that you're looking at. Change in y is equals to v initial plus half acceleration times squared. This is the one that always give you your quadratic formulas, because the c squared if you want to solve for time, which you're going to look at it in as the video progresses. But now we're just going to look at things in a very different way. So normally from your high school, you're taught that a ball is thrown up and it comes down, and you're only looking at one axis. Normally it was your y-axis because it where the ball was falling and coming down. So now we're just going to look at it as in like the ball is in a two-dimensional space. So if it's a two-dimensional space, you know that you should have your x like this, and you should also have your y's. Why? So if you throw a ball, the ball is going to travel in both x and y axis. But in high school, we've been focusing on the ball, or should I say, free falling object on the y axis, because that is where all the interesting stuff was happening. For the y axis, there's not much happening there, because if you throw a ball, the ball on this axis, it doesn't have acceleration, unless if stated otherwise they could say there's air friction and they could give you the acceleration whatsoever. But most of the time on the x-axis there is no acceleration. So you can just use your formulas. The one of the first that I talked about, your d is equals to vt, because there is what uh constant what velocity. along the x-axis. So you could just employ this one because, yeah, unless it's stated that there is friction and friction should come with its acceleration. You get it? Force, remember from your F net is equal to mass. So an object will accelerate in the direction of a net force. So if friction is going, this friction is always opposed. The motion goes this way. That's acceleration will be this way. The case that we're just going to investigate with you here is the case of this ball here that is dropped and comes here. So you know that when something is dropped, exactly, if you drop something, that means you just released it, and releasing it just tells you that the v initial should equals to 0. So we can try to get the height of this building. If there is a ball dropped, we can use one of the formulas that we talked about, of which is change in y is equals to v initial plus half um, acceleration t squared. We can use this formula to get your change in y. But I said the ball was dropped, right? If the ball was dropped, we said something very interesting. I said v initial what is 0. So we know here we have 0 plus half acceleration, because here we're looking at the along the y-axis. If I'm looking at the y-axis, I'm just going to have acceleration, of which is g. Okay, here I should have indicated that I'm looking at acceleration on the y-axis. Now my acceleration is going to be g t squared. Then here I'm going to, with this formula, just going to get the height of the building. The height of the building, I can now equate it. Height of the building, why it goes exactly where there was change in y, because if the ball comes from here to here, that is literally the height of the building. So we can now have a formula that gives us the height of a building, that is can be represented as height is equal to half g t squared. So just because we're working on a 3D space, I did say, so if it happens that you told that something velocity is, you told that, let me say velocity initial is equals to v meters per second. So velocity itself is a vector, right? It has components. This is literally, if the ball, or if this was a ball, okay, let me say this ball was moving up. It was, I don't know, it just jumped up. Okay, so this ball has a velocity along the y-axis, and it also have velocity along the x-axis. Okay, so the v that we call it v initial is the resultant v, of which I can call it a v vector, is a resultant v of both vx and vy, and here it should be given an angle theta. So now we can have vy, we can now get vy is going to be v, um it's here, vy is also here, it's opposite, I can use sine theta, and for vx I can get v cos theta. So this velocity is this very same velocity that the ball is going to use all throughout its motion along the x-axis, noting that um, the velocity along the x-axis doesn't change since there is no acceleration. For instance, if I had a ball that was kicked, as for instance this one, if this ball was kicked and it's moved up and then it went down. So the vx here should equals to the vx here. Why are we saying that? Because the ball doesn't change its velocity along the x-axis unless it is stated that there is a friction, and it should be given an acceleration too. So the for most of our problems, or your exam problems, velocity x initial is going to be the same because there is no change in velocity. Okay, so now with knowing these, you can now Okay, with knowing that Vx is the same as here, you can be required to get V final, of which you're just going to know that you have one side of a triangle, and you also have the hypotenuse. You can do your Pythagoras and solve for the other side. For an example, let me say for the problem that we have, this one that we're discussing, you could be required to get a speed before it hits the ground, like speed before it hits the ground. Let me just write it down. When we want to find the speed before it hits the ground, we really want to find the resultant velocity of both x and y velocity. Remember, when we're looking at two dimensions, we're looking at both x and y component of the velocity, and that will be the velocity that will be given or maybe required to give the resultant velocity. So from what we've discussed lately, you should know by now that along the x acceleration is 0, and along the y acceleration is 9.8 meters per second square downward for me. Yes, downward for everyone, not downward for me. So we remember this thing tells us that the no change in velocity. Acceleration says, okay, if there is no acceleration, then there is no change in velocity. Hence, acceleration is defined by change in velocity per unit time. So now we can, you remember we said these are vectors and they can be represented in terms of their components. We can say now the v final, should I say the v when it hits the ground, should equals to uh, velocity x final squared plus velocity y final squared. That should be all under arrows because we borrowed this from Pythagoras, right? So we can now get the final velocity, okay, of there's the velocity that the ball hit the ground. Remember our Vx, we get the Vx from here, our because it's been not changing throughout. And for our Vy final, we can use the kinematic formulas, look at it on the y-axis, use 9.8 as your acceleration. So on this diagram, we're just going to try to investigate how we can get the height that the ball reached before it hit the ground. Let me call this height. Let me call it C here. I should have said ABC. Let me call it C here. That is going to be the height the ball reached before it came down. Remember, this ball was kicked and then it went boom, boom, and then it hit down, you know? So that is going to, I call this one height, the height. So to get the height, um, we can um, we can employ one of the kinematic formulas that we already know, that is like for a velocity final is equals to v initial plus acceleration time. So we're looking at from here to here exactly. Velocity final, we know that the ball when it reaches its maximum height, it does what? Velocity become 0. It stops and then comes back. It's in the turning point. It's more of like, if you look at it like this is a parabolic function. On the turning point with a gradient of what? 0. Okay, so that's how we look at it. So then you know that your final velocity is 0, but your initial velocity, remember we're looking at this problem in the y-axis. So now for the velocity initial, specifically we're looking at velocity y initial, also velocity final y, and also acceleration y. So along the y-axis, how we made this one? This was supposed to be like this. Okay, so we're looking at y. Okay, then your v initial, we're not looking at this velocity that was given as v initial, but we're looking at the y component of the velocity, of which we agreed that if this y is here, going to be opposite, so it's going to be v sine theta, okay, plus acceleration is 9 is g, okay, 9.8 along the y, right, and time. Then from this equation, we can now get the time that the ball took to move from here, from A to C. So the time that the ball is going to take, we move that to the other side, we're going to have negative V sine theta all over G, that is going to equals to time to move from A to C, to move from A to C. Now we have the formula that we're going to use to calculate time moving from here to here. In the problem, I started trying to get the height of the ball, of which I get carried away and get the time that the ball took it from here to here. But we can still do that. We still have enough time, I hope. So we can just say displacement or change in y, looking at height, should equals to v initial time plus half acceleration, you can call it g t squared. So from this formula now, we can look at it like from the ball comes here from the top, or from C, the turning point coming down, which is the same from coming here to here in terms of distance. If you understand, displacement is not, but we can treat displacement as distance sometimes to perform some mathematical proof. So from here to here, we can call this one h, right? But if you're looking at it like from C to B, is that from 0 to B? I mean, from maximum height, of which is velocity 0. So the initial velocity is going to be 0 plus what is half of g t squared. From here, we can conclude that height can be given as half g t squared. That we can get the height of the ball. And again, please note, we're looking at the y initial velocity from here, y it was here, because in terms of x it was not 0, it was something v's cos theta, yes, and on the y it was 0 because the ball stopped just here before it comes down. That's why we applied, or we could use this 0 for our proof. And g here is an acceleration along the y-axis, so we can employ it. And again, I have to emphasize this one. This formula is used, this is T, okay? Don't confuse it with plus. This formula is used only and only if the ball starts from velocity 0 going down, if it is dropped, or maybe if I'm just looking at it from here to here, from C to B. So I need to highlight that, because if we can get a height of the ball, if it doesn't start here, and we have another formula, we have to explore that in a minute. So in that game, let's try to find let me call this one A, B, C. Let's try to find the height of the ball, the maximum height that the ball reach. So we're just going to employ one of my favorite formulas. F squared is equals to V initial squared, whatever I said, but you know what I said. Okay, plus plus what? 2 acceleration. 2 acceleration, right? 2 acceleration and change in y. So I'm just going to write that in a very nice way, or very formal way to do it. So this, we should be looking at v along y final squared plus is equal to v along y initial plus 2 acceleration along y, and also displacement in y. Let me just call it displacement. Let me just call it h, because we know what we're talking about. We want to find h. So we can find the height now, because we know v final here along the y-axis is 0. The ball stops. So v initial, we did talk about v initial, that we don't exactly taking v as the v initial, but we take the component of v initial. Remember, v could be, v initial is this one exactly, but we're taking the y component. Remember, here we have theta, right? And here we have x, and then we have y component. So we're taking the y, because y is the only one that is taking the ball up to its turning point. So we did discuss that that is going to equal to v, because this is going to be opposite, sine theta, and then plus 2, and for acceleration I'm going to put g h. Then we can find height from here. You can see we're just going to take this one to the other side. It's going to be minus v. Oh, I remember I had squares here. I don't know how I lost it. I had squares here because this has squares from here. Okay, it's going to be v squared. If I put squared inside, sine squared theta is equals to h. Remember h came with 2 here, with 2g, then you're going to divide both sides by 2g. So this is the formula you use to get your height again. If I started from a velocity that will be given, or we don't know in this case, until it goes to a velocity that we know, which is the turning point. Turning point, remember from your math, turning point gradient 0, then yeah, then velocity is 0. Remember, this is the position versus time graph, okay? Position versus time. If it's position versus time, you should know that what is exactly velocity? Velocity, the gradient of this line is velocity, right? So here there is no gradient, right? It's not falling or rising. So literally we're saying, if we're saying no gradient, we mean to say no velocity. Remember, I can write velocity is equals to change in x or change in y, whatever, over change in time. This is just equivalent to gradient, right? So exactly if you're talking about velocity, we're talking about gradient. So here the gradient is high, the gradient is getting slower and slower, and it stops. Velocity 0. And again, I'm just going to look at the range or the reach, whatever they call it. Some people call it a range, I will call it a reach. This is literally the distance that a ball is going to cover, right? Remember we said because there is no acceleration along the x-axis unless given, or in case it wasn't given, it's going to equal to v times time. And we're looking specifically not just any v, looking at v x specifically times time. We know what is Vx exactly. We did talk about that. X is here, it's cos, right? It's going to be V cos theta times time. With those, then we get our reach, okay? The reach is the distance the ball is going to cover along the x-axis. On the past question, we did one of the things that we have proved, we did mention that we can use this formula. Let me just get my ink back. We can use this formula, V final is equal to V initial. If I did copy very well, I don't remember the formula. It was like, yeah, it was like this. And we were looking at the time that the ball takes to goes up and to go up, and then from final we said it was 0, and then initial was something that we don't know, but we know that it's just a component of V initial, of which is V. Let me call this one y, V sine theta, and acceleration was g, and time, that's what we're looking for, right? And what we did, we transport to the other side, we had negative v sine theta all over g again is equals to t. And then we had formula for t, right? We now know what time takes for it to move here to here, okay? But if we need time for the reach, the ball take it same time going up as same time going down, and that is the very same time the ball is going to take moving from A to C. Again, I repeat, the same time that the ball is going to take from here to here is the same time as from here to here. So if this is 1 time, this is 2 time. So this is formula satisfies moving from here to here. To make it to cover for a ratio of which is AC, you have to put 2 just to multiply it, because it's going to be 2 time. You get what I'm saying? You get what I'm trying to say? It's like the time it took up is the very same time it will take down. So it's very same. The sum of those times the same time it will take for its horizontal reach. Now from these lovely formulas, I can substitute one on another, because the range is from here to here, and the 2 time is from here to here. Again, it's time times 2. The time from I'm looking at A to C, and also the reach I'm looking at A to C. So I can now say the reach is going to equals to, let me just remove that. I can now say the reach is equals to V cos theta times time. We're looking at A to C. I always want to say these things so that the marker doesn't get confused. Okay, T. Then now we know the reach is equals to that, but we also V cos theta. We also know time for the reach for AC. Of that time is 2 uh 2 2V sine theta all over G. So I'm not putting this negative sign because literally if I have negative 9 here, 9.8 will take out that thing. The negative will cancel out. I'm putting this in the space of T. So now I can solve or simplify it. I'll have this times this. Oh, if I have V here, I have also V here. Then I can have 2V squared. And I have this and this here. I have sine theta cos theta. If I'm and then that is all over G. But here, if you were really listening on your math class, this thing look familiar, right? It's a double angle. It's a double angle of sine. So we can just take advantage of that knowledge. We can now say reach my ink back. Reach is going to equals to 2v squared and sine 2 theta divided by G. We have another formula for reach. Again, I repeat, the reach is the distance that the ball is covering on the horizontal axis, on the x-axis. Okay, we've been having scenarios where the ball goes up and comes back on the very same height that it was, and it has been very easy to work out because you have that time that the same time it goes up, the same time it comes down. So I also need to emphasize something that I did mention on my videos for projectile. I mentioned something very critical on that video that velocity, when you're talking about projectile motion, the velocity on the y-axis on the same altitude is the same. I'm trying to say literally velocity y a is equal to velocity y k because they're in the very same altitude, height above sea level. So the velocity here is the same as velocity here. So far we've been working in problems that really cuts here, where the ball goes down and comes down again. Very same time up and very same time down. It's been very easy, right? So now let's try if the ball just goes down to some height down. So we do have the formula for time. I think we did calculate the formula for time from here. We did calculate formula for time. I don't know where I put it. Oh, this is the formula for time when it goes up and it comes down. It was very nice and very easy. Let's try to find time that the ball is going to strike the ground. So we can use one of our very good friend, of which is displacement. Displacement should equal to v initial plus v shall t plus half acceleration t. We can use this friend of ours. I think the formula is okay, but here it needs to have a square, okay, because it's one of that quadratic one. But we know something about v. We know something about change in y. Change in y is literally v final minus v initial is going to equals to not v. I just took y, so it's y final. Y final. Just so this v initial to hint me plus half acceleration I put g times time squared. We're trying to find time the ball takes from A to C. Okay, so now then we're just going to take v initial to the other side. It's going to be v initial, it's positive now, plus that is my, when I say v I mean this thing, that is my y initial and the initial that was already here, t times half um, plus sorry plus g times squared. And from this statement we just saw some things very interesting. We know that v final is height final, or should I say displacement final, is here, and we know that here there is no height exactly, there is zero height. Then we can just easily plug in our zero here and make our life very easy. And v initial, we know that v initial is what is our our height initial is the height of the building that the ball was launched. Okay, let me just call it height. I call that let me call it big H. Okay, and that is going to equals to v initial. We did talk about v initial. We know that v initial, we're looking at y-axis, right? Let me put those y's here. Y is everywhere. Y here, y here, y here, y here, y here, y here. So we're looking at v initial on the y. We're looking at the y component for v. So y is like it's the opposite if it was here. So we're just going to have v initial sine theta, right? And we're just going to add half of gravity times squared. Remember, we were trying to get time. Now we can see that this formula can be written in a very standard way for a quadratic, of which is ax squared plus bx plus c. That is your quadratic formula. So if I can order this in a very nice way that you easily recognize it, we have half gt squared. I had some t here that I lost. It was here, and I'll have plus v initial sine t plus h. So this part is a coefficient of t squared, this part is a coefficient of t, and this part is a constant. From that we can see that this one is a, this one is b, this one is c. To find the correct answers for time, we can now use your very powerful friend, your quadratic formula. We can now say time is going to equal to b minus plus root b squared minus 4ac all over 2a. Okay, and again, you know that if you're using quadratic has like two fixes, of which could be a negative or should be a positive. You know that because we're working with time here, you're only taking the positive answer as the correct time, because we can't really have a negative time. And if you really not like me, if you hate quadratic formula, you could use some knowledge that we've proved before in the video. We did prove that we can get time from initial or a launch point to a maximum height, and we did have a formula, and the formula was like t is equals to v sine theta all over g. And if you think I got it wrong, you could just scroll back in the video and confirm for me, but I believe it's okay. This is a formula that we use to get time from here to here. Let me just say it's from a to b. So, and again we can also get a height. We've proved that if I call this one height, if I call this one, now we can get time from here to here, and we can also, so we now have height from launch to maximum height. We do have a formula that we use to show that we did prove in the past, and the formula was like, I think, let me call that height a big H, is equals to the formula is v squared. Remember, it was proven from a formula of v of I think it was v f squared is equals to v initial squared plus I think it was plus 2 blah blah blah. I think, let me just see it again. So this is these are multiplying. We just say h plus big H. Okay, whatever I'm trying to do here, h is supposed to be plus, because we have 1 over 2 here, we could just times by 2 here, and we have times g, we can just divide by g is equals to t squared. We just put t, and here we put the root. I'm very bad at it, but the root, yes. And now we can get t without using the quadratic formulas. On this video, you have covered very important steps of how to prove uh, exactly show how you got into your formulas before you use them, because most of the markers don't really like you just bring up formulas, very interesting formulas like these ones. You can't really bring them up. They want you to show how they made up. Exactly, there is nothing new you need to know. You only need to remember that these formulas that you work the formulas that you worked with in high school, you just have to put or look at them in a component format, should I say. Look at them as x and y. If I can highlight one of the most things or most important things that I think we learned here, we learned that whenever you kick a ball, this is the ground, you kick the ball and the balls go boom. The most important things that you need to note from this motion is that if you kick a ball, you're giving the ball the velocity and the x-axis, and you again you're giving the ball on the velocity on the y-axis. So whenever you're doing your calculations, just know that it depends which velocity you take. If you want to work on the y-axis, like you're working with projectile, you take this one as much as you did in high school. So it's more like the math that you know and the method that you know. Nothing new exactly if you're looking at projectile, should I say, motion in two dimension for this case. So you just have to look at it as like two components. Also the same thing, they can want you to get the final velocity that the ball hits the ground. We have the ball here hitting the ground. You have to take one thing. The velocity the ball hits the ground should be something like this. So if it's like this, obviously again still has that uh, vx component. That doesn't change. Remember we said constant what? Constant constant velocity here means no acceleration. So the velocity here should be same as velocity here. We did emphasize that. And also, oh, that's not all. It also had velocity along the y-axis, and it have another velocity here that goes like this. Remember here, this is velocity itself. This is the vector itself, but this is velocity y, its component. So whenever you're getting your answers in component form, but you expected to represent them and the full vector, or should I say the resultant vector. And also you will have what? Your angle here. So the science is all here. If you can figure out this picture that we're only working with components, then you're all good. And here there's no acceleration, you just work with your simple formulas that is just you just employ the triangle if you still remember it, where you have D here, you have S here, you have T here. You can work everything on the horizontal with that because there is no change in velocity, no change in acceleration. Thank you. Please subscribe if you enjoyed the video. Just put that thumbs up. Thank you for watching.